So my first speaker of the day is Tsachik Gelander. This is the third and final lecture. So let's begin.
Thank you. Okay, so we consider a minus or G a semi-simple, let's say simple Lie group, and it works. I don't want Danny to interrupt. And we want to understand subgroup of G. So we look at the space of closed subgroup of G, and there's a great interest in subgroup, in discrete subgroups, in lattices, arithmetic groups, thing groups, for many years with the application to many fields in mathematics. Homomorphic form, number theory, geometric group theory, dynamics, etc. So these are very interesting objects, the discrete subgroups of Lie groups. And in this course, I am promoting the probabilistic method to approach these groups. And in the first two talks, we discussed IRSs. Invariant random subgroups, so G acts on that space by conjugation, and the probability measure which is invariant under this action is called an IRS. And we show that we can deduce we can prove new theorems about lattices, viewing them as special examples of IRSs. IRSs are more general, but the space of IRS has some structure which you can analyze and prove results about special points there, like the lattices. But since G is non-amenable, in particular, invariant measures are limited. In particular, so many subgroups are not in the support of invariant measures. So you limit yourself. So it's a good idea to look at more general measures. And so today we try to look. We allow to look non-invariant. So that's more general, of course. And so the idea is to look at to consider in particular stationary measure. So this was discussed in PNE course. So we fix mu, a probability measure mu on G, some measure on a generating set or some measure that generates G. And then whenever G acts on a space, G acts on some, let's say, space Y, a compact space. There are many, or there are stationary, mu stationary measures. So these are measured mu it's a probability measure on Y, such that the convolution it's a fixed point under the convolution. And the existence of such measure, for the existence, you just need the amenability of Z or of N. So in the integer is amenable semigroup, you always get stationary measures, and so it's much more general. So we want to consider stationary measure on the space of subgroups. Now, okay, I don't say that any point in any G space is in a support of some stationary measure, but from any point you can start a random walk. So you can start a mu random walk from any point here, and the mu random walk produce stationary measure in the limit. And if some properties are retained by taking limit, you can study the initial point you started with. So even though stationary measures, they have some structure, so they're also limited. So it's not true that you can get completely crazy with them, but you can at least apply them, opt to apply them to start with any point. So in a sense, if we care about discrete subgroup of G, we now have in theory at least a probabilistic method to look at any discrete subgroup. You start with a discrete subgroup. You consider a random walk on the space of subgroup of G starting from this discrete subgroup. So we will consider, we can consider random walk on the space sub G, space of subgroup, or the space of discrete subgroup. So this was an open subset here. So you can start with a discrete subgroup G, gamma in G, and then look at the measure, the Dirac measure supported here, and then convolve this measure with mu many times, and you get a random walk. In the limit, you will get some, if you want, you can take I go from 1 to n, and 1 over n, and then this will converge. Maybe the limit is not unique, but so this will converge to some limit, nu, which will be a stationary measure. It would be a mu stationary measure, and maybe some properties of gamma you can still see in the limit measure. So at least we have a tool now to study every discrete subgroup. So yesterday we had this Stuck-Zimmer, the wonderful Stuck-Zimmer rigidity theorem that tell us that in higher rank, IRS is supported always only on lattices. So we have no use of IRS if we want to study, let's say, manifold of infinite volume or a discrete group of which are not lattices. But now we take any group, and you can start with this random walk and get some measure, and maybe you will see some properties of the group you started with in this measure. So this is
Isn't it clear that gamma will be in the support of this? Like, why not always do this?
No, gamma. Okay, so this measure is supported just on gamma. This measure is supported on conjugates of gamma, because remember G acts on the space by conjugation. So any such measure is supported on the conjugacy class of gamma. But in the limit, you are supported in the closure of the conjugacy class of gamma. And the closure of the conjugacy class of gamma could contain in general a lot more groups.
But it will contain gamma?
The closure, of course,
But maybe the support is in the closure and not like.
The support will not contain gamma. Yeah, the support, if we start with the support will not contain gamma. Unless you started with an IRS, and then the support will be.
Is there some simple example to like maybe suggest that the limit really should have any reflect gamma at all? Like, why? It seems like a very wishful thinking, which I know
Some properties of gamma. Okay, so here is
properties. I see
some properties. So for instance, so now we want to definition. A subgroup gamma in G is called confined if there exists C inside G compact set such that
I guess it's very difficult.
For any element in G, the intersection of the conjugation of gamma by G intersects C by a non-trivial element. Then it's called confined. There is some compact set that intersect every conjugate So by the way, a manifold M, let's say X mod gamma, is called uniformly slim if it has a bounded injectivity radius. So there is some R such that at any point in the manifold we have a loop, a non-trivial closed loop of length less than 2R. So an R ball you cannot inject an R ball in this manifold. Then it's called uniformly slim. And an exercise gamma is confined if and only if suppose it's discrete, X mod gamma is uniformly slim. So it's the same thing. And confined is a notion that was studied also for discrete groups long ago. So in discrete group, you ask for a finite set which intersect non-trivially every conjugate of the subgroup. Here it's a compact set. Sorry?
If the C doesn't contain one, won't that intersection just never be?
No, you want -1 is not the empty set.
Yeah, thank you. Thank you. So it's intersect by a non-trivial element, intersect C by a non-trivial element. I don't care if C contains one or not. The one doesn't move when you conjugate. So here's here's another exercise. If gamma is a lattice, lattices are confined, or if you want, lattices are confined. Equivalently, finite volume manifold is uniformly slim. But it's obvious because large ball has large volume, right? So if you take a radius such that the volume will give you something larger than the volume of the manifold, then
It's obvious for every locally compact group, or when you have some space, you have.
here you have a space. It's in homogeneous space, and it's obvious. Let's talk later about.
I'm not clear what this is saying. Like what? Like there's some quantifiers or something missing that.
No, it's because of that. It's not quick.
No. Okay. Exercise 1, exercise 2, which is simpler, but the exercises are equivalent. I mean, this fact is equivalent to that fact, and both of them are true.
Got it.
And okay, so let's see an example. So suppose that rank of G is 1, so it's like SON1, SPN1, etc. Gamma inside G uniform lattice. So it means that this means that G mod gamma is compact. So it has finite volume, but it's more than that. That's the definition of uniform lattice. And the G mod gamma is compact. Every simple Lie group admits uniform lattices, non-uniform lattices, and a lot of them. That's a classical theorem of Borel. So gamma is a uniform lattice. It's hyperbolic group. So global hyperbolic group it admits let delta inside gamma be non-trivial normal subgroup of infinite index. So gamma mod delta is infinite. So it gives you an infinite volume manifold. X mod delta will be a manifold of infinite volume, and that so then delta is confined. Since gamma is compact fundamental domain, you enlarge this compact fundamental domain a bit. So whenever you conjugate delta by gamma, you return delta because it's normal. So you just need to consider this conjugation by the compact fundamental domain, but of course you cannot escape to infinity if you conjugate, right? So if you have a normal subgroup of infinite index, then it gives you a discrete subgroup which is confined. And now I understand the question. Something is missing. There was.
Oh, on the left, on the right of the board.
Okay,
Yeah, I see.
okay. So there was a conjecture of Margulis that this cannot happen in high rank. The Margulis conjecture that if rank G is at least 2, then a confined subgroup is a lattice. So if you have a subgroup such that you have a compact set that intersects not trivially every conjugate of it, it must be a lattice. You see, it is stronger than the normal subgroup theorem by this example. If you have a lattice and you have a normal subgroup of infinite index, it will give you a confined subgroup which is not a lattice. So if this is true, it implies a normal subgroup theorem. So this conjecture is equivalent to the fact that infinite volume manifold infinite volume manifold of rank at least 2 are not uniformly slim. They have unbounded injectivity radius. Inside such a manifold, you can see if you try to draw a manifold of infinite volume, so it has infinite volume, but if you go far away, you will see large ball. You can. It cannot be like uniformly slim like the infinite line that the infinite uniform. Yeah, like what I drew yesterday in a parabolic case. So it must be. So that's the conjecture. And
So the conjecture is the converse of the exercise.
yeah, this is rank 1, and in rank 1 it is not true.
Yeah.
And in higher rank it is true. So let me give another short exercise. Let's say delta in G, a subgroup, is not confined if and only if you can approximate the trivial group by conjugates of delta. So if you look at the conjugacy class of delta by G, you take its closure in the Chabuti topology, in the topology of closed subgroup, this will contain the trivial group. If you can approximate the trivial group, it means that you can escape from any compact set, which is equivalent to say that you are not confined. Okay, so the theorem that Mikowai, Tsachik, and me proved is that this conjecture is true. Theorem. So let G be a simple Lie group of rank at least 2. If gamma in G is a discrete subgroup of infinite covolume, okay, if gamma in G is confined, then gamma is a lattice. Equivalent if gamma is not confined, then it is if gamma is not a lattice, if the manifold is not a finite volume, then it's not uniformly slim. So that's the theorem that we pulled. So once I prepared the slides to my talk, to another talk, and I wrote a theorem and I wrote this G, and my wife checked the slides as I asked, and she asked me what is this G, and I said G is from Gelander, and I said, so why do you say that G is a semi-simple ligand? Okay. And to prove this result is by random walk. So that's coming back. So you start from a point on the manifold. You want to prove that the manifold has the R thick part, that the R thick part is non-empty, and the idea is to apply this mu random walk and to check yourself and to see that the mu random walk must visit infinitely many times. Most of the time, actually, must spend in the thick part. Otherwise, something wrong must happen. So that's the idea. And so the idea is to consider again this random walk on the space of discrete subgroup. Now, when you consider a random walk, you have to choose mu, and this is delicate. You have to do it wisely, and but you have some advantage here because you can change mu along the way. You want to prove something, and you start with one mu, and then you change to another mu. So how to choose mu? Mu. So the generator measure on G. So luckily, so a couple of years ago, jointly with Margulis and Ariel Levy, we proved the effective version of the Kasdan-Margulis theorem, and for that we had to generate. Okay. So the idea is the following. So there is a measure mu. There is a measure. So, and more specifically, mu will be the following measure: eta k, delta s, eta k, where this is a R measure on the compact group K. So we fix a maximal compact group, and you can take the R measure on it. Now S is a semi-simple element in G. So if you don't familiar with Lie groups, so if you consider SL3 SLNR, then you can take a diagonal element, a semi-simple element which with some property. So the property that I need is that it expands by a lot when it's act by conjugation on the unipotent radical of a minimal parabolic. So when you translate it to SLN, it means that AI is much bigger than AI plus 1. And there is a quantitative, everything in the work with that we did with Margulis and Levitt is very specific because we wanted specific result. So there is some specific condition here. And then we get a measure which is nice enough. And with respect to that measure, we proved a theorem about okay. I will tell you the fundamental lemma that we proved. So you consider the discreteness function. So that's a function on the space of discrete subgroups. So let G be the Lie algebra of G, and we suppose that we have a norm on G, and suppose that the exponent is well defined on the ball of radius 1, and then you define the injectivity radius or the discreteness function of a subgroup gamma to be the supermum over all R less than 1, such that the exponent of the ball of radius R around 0 in the Lie group intersect gamma trivially. Basically, you look at the Lie group, you look at the around the identity in the neighborhood in R in G, and you look at the largest ball of radius at most R, such that you don't see element of gamma. So in a sense, it's measure the discreteness, how discrete is gamma. So it's some function that measure the discreteness of gamma. It can be at most 1. So a group can be at most 1 discrete. If it's more than that, we don't care. It just tell you information about small injectivity radius, not about large injectivity radius. And then the theorem that we prove with Arielevich and Margulis is that there exists a positive delta, a number C which is smaller than 1, that's important, and a constant B, everything is computable, such that if you take that mu, such that the integrals of I to the minus delta of gamma to the G d mu G is smaller than C times I to the minus delta of gamma plus B. This is the equation that we prove. If you convolve, if you convolve with this specific mu and look at the injectivity radius, the injectivity radius must, in average, increase in some way. That's the fundamental lemma that we proved. So it's really powerful. There are a lot of applications of that. So and we in our paper we calculated everything explicitly. We calculated mu, we calculated S, we calculated delta, we calculated C, we calculated B because we want the effective estimate. But for the work here, I just care that this C is smaller than 1 and that such mu exists. So there is some measure mu that in a sense increase discreteness. If the discreteness is too small, then it will increase this. Somehow it prevents you from spending too much time in the thin part of a manifold. If you do random walk on a manifold, with respect to that measure, when you go to the thin part, it will put you out. That's the idea. Okay.
The integral is over all of G, right?
The integral is over the support of mu. Mu is supported on a compact set.
Oh,
Mu is this measure. R measure on Q, convolution with Dirac on some element, and so mu is the bind. So this measure mu is not smooth, but so we apply to do random walk and we care what's happening in the random walk, and then at the end we get some stationary measure in the limit. And to analyze the stationary measure, we actually prefer to work with smooth measure. But that's another advantage of stationary measure. They don't really care what is the original measure mu, they just care about the Poisson boundary. So if you consider only bi-invariant measure, then we know what is the Poisson boundary, and we can say things about. Okay, let's do it in a moment. So how do we prove this theorem? So the idea. So I'll call it delta to emphasize that it's not a lattice. So let delta inside G be a discrete subgroup of infinite volume. So it's not a lattice. For instance, infinite index subgroup of a lattice, but much more general than that. Consider the Dirac measure on delta, and consider and define nu n to be 1 over n, this Cesaro sum, n goes from 1 to n of mu I times convolution with this measure. So this gives, we look at the random walk on the space of discrete subgroups. And then we take the algebraic average, and we want to see what happened. So the theorem that we prove actually is that this converge to Dirac of the identity.
Nu n.
Yeah, thank you.
And in the definition of nu n, the delta subscript should be the capital delta? Or?
Okay, thank you. So we start with Dirac measure on some discrete subgroup. You do this convolution, you get random walk on the space of discrete subgroup, you take ergodic average, and there is a limit, and the limit is Dirac measure on the discrete group. If you think geometrically what it means, it exactly means that if you do the corresponding random walk on the manifold, you spend most of the time in the R-thick part for every R. In particular, the R-thick part exists. So that's a theorem, and the proof, I like to think of the proof as a three-step proof.
So this immediately implies the not confined.
Yes,
yes.
Because the limit measure is supported on the closure of the conjugacy class, it means that the trivial group is in the closure of the conjugacy class, and therefore, yeah. So this implies the normal subgroup theorem and much more. So
in this case, it doesn't capture like any of the properties of the original.
sorry?
So in this case, it's not that the limit captures some of the properties of the original group.
Yeah, it does.
And it's discrete.
No, it means that the original group is not confined.
Oh.
That's the property that I'm after.
Is that closed property?
Yes, yeah. That's another exercise for you. If you have a confined subgroup, then all this group in the closed conjugacy class are confined. There is a compact set that intersect non-trivially every conjugate of a group, then it intersects also every limit of a conjugate of that group. Yeah. So so it retains. So this property specifically is retained in the limit. So and the three-step, the proof, 3 steps, which I think of them as first it is discreteness. Second, stiffness, and the third is rigidity. So the discreteness is what is the consequence of this fundamental lemma. The consequence is that if you apply this random walk with this measure, with this specific measure, then the limit will still be discrete. So at the beginning, you don't know that there is a limit. So now, okay. The beginning, you don't know that there is a limit. So by the way, so this theorem is any semi-simple group. So let G be semi-simple. It could be SL2R or SL2 times SL2, etc. Okay, let's delta be in G discrete. Let nu infinity be a limit, a weak star limit of nu n, which is 1 over n mu to the I convolution with that. And then nu infinity is supported on discrete subgroup. So you see, this is the open subset of the space of closed subgroup. So it's not obvious that a limit of so you can have in general you can have measures which are supported on discrete subgroup, but in the limit you get some non-discrete subgroup, and that's a problem for us. And that's this is why we work with this specific measure. This specific measure we will not let the limit to be non-discrete, because whenever the injectivity radius is too small, it pushes you out. So that yeah. So that's the first step. The limit is supported on discrete subgroup, and that's it for any semi-simple groups. The second step is stiffness. Stiffness means that stationary is invariant. So I started the propaganda by saying that stationary are much better, they're much more general, and now I tell you that. Okay, not exactly.
So the property you just erased, does that mean that somehow that guy and its convolutions live in some closed subset? That's why that's the same. That's what you proved.
The property,
That you just erased this like
fundamental lemma, what I call. No.
But that seems like what this theorem one is saying. Well, I mean, no, these are specific new measures, but.
Okay. Yeah. At the end of the talk, I can elaborate more about this theorem, about some how to interpret it. It actually takes some time to grasp this theorem. Yeah, there's all. For those of you who know who comes from homogeneous dynamics, so there is this thing that's called Margulis functions, which is a very useful tool for many applications. And what we proved is that you can the injectivity radius, you can define a function that is a Margulis function and somehow detect the injectivity radius. Or discreteness, and deduce application from that. But I can come back to that later. The second step is stiffness, is the following theorem. So let G, let's say G1. I want it not to be simple because it's more interesting to state it in that case. G1 times Gn. Semi-simple. Let say nu be a probability measure on the space of discrete subgroup of G, be a stationary measure, mu stationary measure, such that almost surely the subgroup intersect trivially every rank 1 factor. So if G doesn't have rank 1 factor, then there's no assumption here. Otherwise, if G has some SL2 or R, SL2C, SON1, you want the intersection of gamma, where gamma is a random subgroup, to be trivial with that factor. And that's some irreducibility assumption. You can actually give weaker irreducibility, but we need some irreducibility assumption, otherwise it's not true.
Is he stationary with respect to that particular mu or?
Yeah, it's stationary with respect to that particular, but for the proof, I'm using smoothness, and that particular was not smooth. So the point is that if you, yeah, it's stationary with respect to mu. Mu is stationary, but I will remark about it in a moment. So you have such a nu, then nu is an IRS. So that's what we prove. So if you have a stationary measure, it's actually invariant. So you start with a random walk, and at the end you get some invariant measure. So that's the theorem. And what you asked about mu. So the proof relies on the classical work of Nevo and Zimmer, a really beautiful series of works from the beginning of this century about stationary measures in higher rank, and they use smooth measure. Now, this measure is not smooth, but it's by K invariant, and the thing is that. Okay, let me tell you the short remark about stationary measure. If you have two measures, if mu1 and mu2 are measures on G, probability measure on G, such that they have the same Poisson boundary, such that they have the same let's say B nu 0. Both of them have the same Poisson boundary. Then for any G action, G acts on some space Y, a probability measure nu on Y is mu1 stationary if and only if it is mu2 stationary. To be mu1 stationary or mu2 stationary, it's not a property of mu, it's a property of the Poisson boundary.
When you say they have the same Poisson boundary, does that just mean they have the same harmonic function?
The same space and the same measure. Poisson boundary is a measured space, so it's a space with a. So this is a stationary measure.
So it's equivariance, like measurable isomorphism.
What?
Yeah.
In the same space.
It means that the actions are the same. Like
Yeah. So let me tell you, in my case,
Some harmonic functions, okay.
In our case, B is G mod P. The Poisson boundary of a semi-simple group is G mod P, where P is a minimal parabolic, and nu, the Poisson measure is the only K invariant measure on G mod P. So since my measure mu that I'm working with is by K invariant, the stationary measure on G mod P will be the only, there is a unique K invariant measure here because K acts transitively on G mod P by the Iwasawa decomposition for those. So I thought that you're all very familiar with Lie groups. So there is a unique K invariant measure here, and that's the Poisson measure. And that will be the Poisson measure for every mu which is by K invariant.
What is Y?
Any compact G space.
So it's in general a theorem that gives you
The theorem of Kirstenberg that tells you that if G acts on a space Y, I call it Y, but you can call it X. So G acts on a compact space. A measure there is mu stationary if and only if it's the barycenter with respect to the Poisson measure of some map from the Poisson boundary to the space of probabilities measure on G. That's a theorem of Fürstenberg. And from that theorem of Fürstenberg, this remark follows. The remark tell you that to know what is the stationary measure, we can forget about the original measure. We just need to know what is the Poisson measure.
if you have two
So
measures with the same Poisson boundary, then their stationary measures
Yeah.
are actually any compact measure will be
Yeah.
the same.
at the same, yeah, and I consider G, and I consider some simple group, and I consider only by K invariant measure. Actually, so far I consider only one of them, and this I consider this one because with respect to this one I can control the random walk. But once I control the random walk, I can forget about this measure, and I only look at stationary measure. Now, when I work with stationary measure, I prefer that the original measure was smooth, because some theorem needs that. Sometimes you need. But then I say, okay, I don't care about the original measure. There is another smooth by K invariant measure. You can easily write a formula for a smooth by K invariant measure, and now with a smooth measure, you can apply the theory, the wonderful theory of Neveu and Zimmer specifically, I refer to two papers, one from '99 and one from 2002. Both of them, I think, one in Invenciones, one in the Annals. One wonderful paper that tell you it's extension to stationary action of Margulis factor theorems. Basically, they tell you that every stationary G action on every space, either it is invariant, the measure is invariant, or there is a non-trivial parabolic factor. And when you combine this information with the fact that you know something about the space, the space of discrete subgroup, you can prove stiffness with that. So it's really the deep thing behind this theorem is the work of Neveu and Zimmer, and we just applied it to our situation. Now you can apply the rigidity theory that I already mentioned yesterday, the Stokes-Zimmer theorem, and etc. Because now in the safe ground that we know invariant random subgroup, we show that from any discrete group you can cook an invariant random subgroup, but there are not so many invariant random subgroups. So you start with a discrete group. I just wave my hand and say you start with a discrete group, and in the closure of a conjugacy class, you found some IRS. How can it be? So we found lattices in the closure of the conjugacy class of it. by Stuck-Zimmer theorem, there must be lattices, all the trivial group or lattices in the closure of the conjugacy class. But now lattices are locally rigid by a theorem of classical theorem of Selberg, Weil, and Calabi. So lattices are, or in this case of Weil and Margulis. So lattices are locally rigid. Then that cannot happen. So the only so from local rigidity and the stiffness and Stuck-Zimmer, we deduce that the limit must be the trivial group. So that's the result. And so this result implies the normal subgroup theorem. It implies the seven samurai theorem. It has various applications. Now, yeah, again, there are some things that we don't know. Let me spend the last few minutes to discuss rank ones. So this theorem tells us again in higher rank, every stationary random subgroup, discrete stationary random subgroup is also invariant random subgroup. What going on in rank one? So that's more mysterious. In rank one, there are non-invariant, non-IRS, stationary, discrete. By the way, if you don't, non-discrete, they're also in higher rank. G mod P admits, of course, stationary random subgroups. Yeah, the stationary measure. G mod P is the Poisson boundary. It has stationary measure, which is not invariant. There's no invariant measure on G mod P. So there are non-invariant stationary, discrete stationary subgroup. And the construction is as follows. I'll explain briefly, and maybe Gil will give more details. So we start with a free group, let's say on two generators. That's a free group, A inverse, B inverse, and so on. That's the Cayley graph of free group, and this is a four regular tree. And then no colors.
There are some.
And then you add, you pick one point at infinity, and you construct the so-called grandfather graph or grandmother graph of this graph. You connect every vertex to a vertex which is two steps closer. So there is one here, and so you connect this to that, to that, to that. So then you get then if you do it, you will get a graph which is a 14 regular graph, because I added 10 edges from this point, and from any point you had one that get you closer to the special point in the boundary, and 9 that get you further. Now this 10 regular graph is also this red part of it consists of two components, one for even on the odd vertices, and each of them is a 10 regular tree. And so it's not hard to give it to decorate these edges by colors and make it a Cayley graph of F7. It's a 14 regular graph, which is actually not a Cayley but a Schreier graph of F7. Now, okay, you get a Schreier graph of F7. So you get a subgroup of F7. You can start a random walk from that subgroup on the space of discrete subgroup of F7. In the limit, you will get some stationary measure on the space of discrete subgroup of F7. I mean, all subgroups are discrete. So you get some stationary measure. This measure cannot be invariant. Why? Because there is, from every such group, there is a special point in the boundary of the tree, of the original tree. So you can, there is a map from this measure, you can push it to the boundary, and if this measure was invariant, you would get invariant measure on the boundary on the tree. So by this way, you can cook a non-invariant stationary measure in the free group, and you can also, now since the free group is a lattice in SL2R, you can also embed this subgroup as a uniformly slim, as a confined subgroup in SL2R, and take the stationary limit of the random walk that we discussed before, and you get a non-IRS stationary random subgroup, discrete stationary random subgroup inside SL2R, and inside actually every, you can do it in SON1 or whenever you have a Lie group with a lattice which project onto the free group. Then you can do it, but I don't want to do it in SPN1 or I don't want to do it in more generally. And also, I don't know. I mean, I think it's very interesting to analyze what are all the stationary subgroups of the free group of SL2R. It's really, I think, fascinating. And in particular, do you have something like that in SPN1? SPN1. So I think my student, mine and Uri Bader's students, they call these groups higher rank one groups. So they are like they are rank one, but they are rigid. They have super rigidity, arithmeticity, property T, etc. So they have properties of a higher rank group, but are still hyperbolic. So they don't have the normal subgroup theorem, but they do have other things. So what's happened here? It's more mysterious. So do they have stationary random subgroup which are not invariant? Yeah, thank you.
All right, do we have any questions? I have a question. So from what I can tell is formally your theorem doesn't formally imply Stuck-Zimmer. It uses Stuck-Zimmer, but is there a natural generalization that maybe you haven't, or that's a conjecture or something that would actually be somehow encapsulated? Because you mentioned it doesn't imply Margulis normal subgroup.
Yeah. If you, of course I try to simplify everything. But if you look in our paper, we prove Stuck-Zimmer for stationary measure in that context.
Okay.
So we proved it, but again, of course, we relied on property T. We couldn't do cases that, of course, we relied on their on the original Stuck-Zimmer. So
got it.
So yeah, it's Stuck-Zimmer for higher rank semi-simple Lie group, also for stationary.
Got it. Okay.
Under some irreducibility. So, yeah, now I can say more about this Margulis function, but maybe yeah.
Well, so we the schedule says that we have to end now. So during the break, people can ask that.
Thank you.
Thank you.
Guys are looking at me like